All right, ladies and gentlemen, you are welcome once again today. We want to look at the application of the principal component analysis. This is a data set you all have. This is a data set which we have. The first thing to do is to take this data set to R. Okay, let's take the data set to R. How do you do that? You have the commands here. The presupposition is that you have all of these commands already. So you type this command into R, and then you go to the data. Okay, so now let's go to the data in Excel. This is the data in Excel. In Excel, when you click anywhere inside the data, do Control A to highlight, Control C to copy. And then once you copy, you go to your R Studio. You type the first command, which is the example read.deleme clipboard, and then run it. When you run it, you just highlight the EJ alone and run that as well. When you run that, the data will be shown down here in the console. So that means that your data is loaded. Let's plot a scatter plot. Okay. By using the command plot EG, the color of the scatter plot must be blue, and then the line width must be 4. Okay. The line width must be 4. Okay. That is how it's supposed to be. Okay. So let's do a scatter plot of the data, and you expect the results to show on the right side here, on the right side. So once you do that, wow, now you can see on the right side, the entire scatter plot is showing. So this is a scatter plot. It tells you the relationship in a picture form, the relationship between each variable and the other. So as an example, okay, as an example, suppose I want to look at the relationship between this variable 1, okay, and then the variable 5, okay, variable 1 and variable 5. I will go this way and that way, and they will meet at this junction. So this scatter plot here, okay, that scatter plot here, this is the one that is going to help me to know. Scatter plots are good, but the thing is that they don't tell you a numerical, value. So even though you know that there is a negative relationship between the variable 3 and variable 4, if you look at it, there's a positive relationship between variable 3 and variable 4. This value is showing it. Okay, this value is showing that. Even though there is a positive relationship, how much positive is positive, you don't really know. And so what you do now is to go and generate the correlation matrix. All right. How do you do that? It's a very simple thing. So let's generate the correlation matrix. And one way to do that is, one way to generate a correlation matrix is by using the command round, this command here. Okay, round core example. Now that round, it means that you want the results to be in 2 decimal. So the round means correct to what decimal places? Round it to 2 decimal places. Other than that, it would have been just call into brackets the name of the data set. So you run this thing, and then what happens is that you now have the correlation matrix. That's what's down here. So you have your correlation matrix down here. This is a correlation matrix. And once again, when you go to the data set in the slides, this is a correlation matrix. Then I'm about to ask you some 5 questions from this correlation matrix. So if you know the answer, just raise your hand for me, and let's get to rock and moving. So who can tell me the correlation coefficient between variable 4 and variable 5? What is the correlation coefficient between variable 4 and variable 5? Who can tell us? Who can raise a hand, or who can type the answer for me? Between variable 4 and variable 5. Ebenezer Kwame Atta, let's see. Hey, Ebenezer Kwame Atta. I think I know this person. Let me see. Ebenezer, can you share your answer with us, Ebenezer? Yes.
Dog is 0.5, negative 0.50.
Negative 0.50. That's it. You're right. You're right. So that is it. You can easily tell. Let me ask one more. The easiest part. What is the correlation coefficient between variable 6 and variable 2? Variable 6 and variable 2. I know many of you are cracking it. If you know the answer, you type it. 0.69 is the right answer. I think many of you have got it now. Now, those are preliminary. They are not really the answers. Now, let's get going. The first most important question is this: using the rule of thumb in principal component analysis. This means that there's a rule of thumb. Using that rule of thumb, which variables appear to be strongly correlated with variable 1, and then with variable 2. So, ladies and gentlemen, this is the rule of thumb. The rule of thumb always says something. And this is where you got to pay attention when it comes to rule of thumb. The rule of thumb always says that for a variable to be strongly correlated with another variable, the correlation coefficient must be 0.3 or more. Okay. The correlation coefficient must be 0.3 or more. So now, using this rule of thumb, which variables appear to be strongly correlated with variable 1? With variable 1. You have your results, I have mine. Dan Owusu Amponsan, let me go to, yes, Dan. Tell us the answer. Which variables appears to be strongly correlated with variable 1?
Okay, Doc, please, it is 3 and 4.
In order.
Yes, so right? It is, yes, please. So the 3 is 0.95 and the 4 is 0.92.
Correct. So anytime you mention the variable, then you put the coefficient into bracket. Excellent. Beautiful. That's it. So those are the variables that are highly correlated with variable 1. Excellent. Now, which variables are highly correlated with variable 2? Because the question was not only on 1, but also 2. With variable 2, which variables are strongly correlated with variable 2? You can tell us that. Selena. Which variable are strongly correlated with variable 2? Yes, Selena.
The table is not showing.
Okay, you want the variables? Okay. The table is showing now. Which variables?
Showing.
Okay, it's taking time.
It's still not showing.
Well, then it means that you don't have your own, isn't it? So normally you should have your own. Let me go to Maclay. Maclay, tell us which variables?
Variables 5 and 6, and for variable 5 is 0.43 and variable 6 is 0.6.
Maclay, I want it to be in order of importance. So say that again.
Variable 6 and variable 5.
Correct. That's how it's supposed to be. Okay. And then, of course, the numbers will come into the picture. So, guys, it's always important that whilst I'm doing these things, you're also doing yours. And it helps you to be able to move on. So that's it. Those are the answers that you indicated. Okay. So, let me see. Variables are strongly correlated with variable. Okay. Okay. So I brought other factors in here, like you see variable 1. Okay, so for variable 1, you have 3 and 4, and for variable 2, you have 5 and 6. All right. Now, the next thing is from the matrix, and listen carefully. From the matrix, is there a basis? These are some of the questions I do normally ask. Basic questions like this before we build up. From the matrix, is there a basis for principal component analysis? You can say yes or no, but you have to justify. Ladies and gentlemen, there advice is that for there to be a basis for PCA, then there must be at least a certain number of correlations, okay, that are, there must be at least a certain number of correlation coefficients that are more than 3, or let's say that are 3 or more, or there must be at least one that has a correlation coefficient of 8.8 or more. So there must be a correlation coefficient of 30% or more at, what do you call it? A correlation coefficient of a certain number, okay? A certain number having more than 0.3 or more coefficients. Okay. And that certain number is supposed to be 7. 7. I need to just verify and confirm. Okay. But at least you need one, at least one of them, one of the coefficients to be 0.8 or more. Then there is a basis for principal component analysis. Okay. So let me just show that. So looking at the table now, is there a basis for principal component analysis? So it means that you must be able to count how many of the coefficients are 0.3 or more. And if you get 7 being 0.3 or more, you're good to go. So how many did you count? How many have you really counted? Letitia. How many have you really counted? Yes, Letitia.
I'm still counting. I've counted.
Okay, I said counted. I didn't say counting. So you don't raise your hand and actually count with me. Let's go to Dan. Nicholas. Nicholas was not ready. Okay. Let's go to Grace. Grace, how many?
So please, I counted 12 without the perfectly correlated.
How many have you counted? The perfect
12.
are not part of it.
Yeah, 12, please.
12.
Yes, please.
All right, you're not so. So is there a basis, by the way?
Yes, please, based on the analysis.
Okay, that's fine. There is a basis, but I don't think your counting is correct. There is a basis, but your counting is not correct. Let's go to comfort. Comfort, is there a basis and what is your justification?
Yes, please. I counted about 14 coefficients with
Yes.
0.3 or more.
Perfect, that's the answer. So the answer is that there are 14 coefficients that are 0.3 or more, and that is more than the standard of 0.7. And so there's a basis for that. Okay. So at least 7 are having a coefficient. And then of course you could see that one of them has a correlation coefficient which is bigger than 0.8. Where is that? If you look at this one, you can see variable 4 and variable 3. Okay, it has that. Variable 3 and 1, you know, several of them have got a correlation coefficient of at least 0.8. The point is that if it happens that you don't get a 7, okay, if it happens that you don't get 7 of them, you know, having a correlation coefficient of at least 0.7, 0.3 or 30%, if you don't get 7 of them doing that, but you get even one having a correlation coefficient of 0.8 or more, there is still a basis for principal component analysis. So you want to understand that part. There's still a basis. But the key point is that if you get that 14 in this context, if you get a 14 wrong, you'll be wrong. And so you don't want the 14 to be, you don't want to get it wrong. You don't want to get 13. You don't want to get 15. You want to get 14. So that means you're going to open your eyes and count them. And remember, you're not counting anything above the right diagonal of 1, 1. So if you're counting at the below the diagonal, focus on that. If you're counting at the above the diagonal, focus on that. So you don't want to count anything, that is both above and below the diagonal. It has to be above it or below it. So that point is very important. Okay. Now, any question on this before we move on? All right. So, but you see, using the number of correlations that are 0.3 or more is not enough. It's important to ensure that the correlation is significant. Okay. David seems to have a question. Okay. So David, you have a question. Go ahead.
So if you use the diagonal,
David, you sound a bit far.
Sorry, sir. If you use the diagonal, then the count is 7. It shouldn't be 14.
Yeah. That's really good, and that's a very commendable thing you just brought up, because that's what I wrote, isn't it? I think that I was enjoying. So it's 7 of them that are actually 0.3 or more. So you don't have to double it. Please note that you don't need to double it. It's 7 that are having a correlation. So that means that there is a basis. Okay. Because the whole idea is that at 7 or more should be that. And then in this case too, we have 0.8. So please guys, it's 7 and not 14. It's 7 and not 14. Excellent. That's a clear indication that this gentleman is really sitting down and he's not standing. Okay, he's sitting down and not standing. All right, let's go to the next thing. So we are going to generate the p-values. We are going to generate the p-values. And to do that, you need this command, which is require or library H miscellaneous. Okay. So we're going to take this and then type that into the R Studio. So you go to the R Studio and you type require or library H miscellaneous. Okay. And then that is under the assumption that you've installed this. And then you run it. Okay. So you can see that it's now installing in my case. Okay. So now it has loaded. With that loaded, you now go ahead and then type this command in order to get a correlation with p-values. Okay, so that's what you're going to type here. You're going to type rcore as dot matrix, and then you generate the Pearson's correlation coefficient. So let's go and do that in R. So you type rcore. Okay, rcore into brackets, and then you type as matrix, as dot matrix, and then after typing as dot matrix, you write the name of the data set, which is EG, and then after that you do a comma and then you write method, EG into comma method, and then the name of the method is Pearson's. Okay, so you do Pearson, and that's it. So once you have it typed, then you run it, and that will give you that. Look down there in the console. Okay, look at the command I just typed, and then it gives you the correlation as always, as before, but also it gives you what? The p-values. So even though you may have identified a particular correlation to be 0.3 or more, you've got to determine whether they are significant. So let's say you identify 0.95 to be significant, to be the variable between variable 1 and 3. Then you have to come down here. And then when the p-value is less than 5%, it means that that correlation is significant correlation. And so you can see clearly that it is 0. So it means that it's significant. The next one is variable, the coefficient of 0.92 between 1 and 4. You come down here, it is also approximately 0. So it means that it's significant. Okay. Now the other ones here, they are not even 0.3 and above. So you go to the next one, which is 0.43, which is between variable 5 and variable 2. 0.43. Okay. And then variable 5 and variable 2, you can see that even though it is 0.3, it's above 0.3. Is it significant or is it insignificant? Okay, this one you have to type into the search. Significant or insignificant? Grace Teta, you said you have a question. Let me see. Grace, you have a question? Let's go.
Yes, Doc. So please, initially you're making a statement after we did the finding the basis for the PCA, but I think you have answered it with, you were saying that it is not enough to know how many of them, but I think the p-value answers it. So.
All right, okay. So it's not enough. So the p-values here. So you when you have something like this, you will indicate that you are going to indicate that there are 7 correlations that are 0.3 and above. Okay, that would have been a basis for principal component analysis. However, this number are not significant. So we have now identified that the coefficient 0.43 here is not significant. Okay, you can see that it is, the p-value is almost 22%. It should be 5% or less. So that shows that that one is not significant. And then when you go to the second one, which is 0.69, look at 0.69. 0.69 to the p-value. If you look at the p-value, that one is 3% when you round it to 2 decimal places. So that is significant. So right now, the only one that is not significant is 0.43. Let's move on. 0.8 is between 4 and 3. Okay. The p-value is 0. So that is significant. The next one is negative 0.42. The p-value is 23%. So that is not significant. So 2 of them are not significant so far. Then you go to the last one, which is negative 0.5. Okay. And when you look at that, its p-value is 14%. So that is not significant. So how many are significant and how many are not significant? How many are significant? How many are not significant? David. How many are significant and how many are not significant?
Okay,
Yes,
Doc, we have only 3 of them that are significant. No, 4 of them that are significant.
Exactly. Okay. So you have to talk about both. That 7 of them have a correlation coefficient more than 0.3. That would have served as a basis for PCA. However, only 4 of these 7 are significant. And since the rest are not significant, in the context of this, there would not be a strong basis for PCA. It's important to put that across. It's important to put that across. Even if the examiner is going ahead to do PCR, it's important. So use the correlation coefficient, but also use the p-value. And you got to know numbers. It's numbers we are dealing with here. It's not just guesses. It's true numbers that we are dealing with here. Okay. Excellent. So 4 are significant, 3 are not significant. That is how you do the first part of the question with the p-value. Okay. And so you can see that when the p-value is less than 5%, then it's significant. Having done this, Latifa has a question.
Hello, sir.
Yes.
Please, I don't get the significant and insignificant parts for this PCA.
Okay.
You can move again.
Yeah, let me go back. So when we say, you got to look at my table here. If you look at the table, the bottom table has P written. That's a P. Okay. And when you look at this P, it shows that everything below it is a P value. But everything above the P is the correlation coefficient. So you have correlation coefficient at the top. And then every correlation coefficient, there is a matrix of its correlated P values. So if you look at a particular variable like this, 0.95, which is a coefficient between variable 1 and variable 3. Okay, let me see if I can beautifully connect you here. So if you look at variable 1 and variable 3, okay, this is 1 and this is 3. This is where they meet. And the value is 0.97. So what you are now going to do is that you're going to connect the same thing. You're going to look for the same thing for variable 1 and then variable 3. See, they also meet here. So this value will be indicating their corresponding P values. And when you look at that P value, and it is less than 0.05, then it means that that 0.95 coefficient at the top, that variable that you see at the top here, that variable 0.95 is significant. If its corresponding p-value down here is less than 0.05. So it's not a matter of just identifying variables are 0.3 and above, 0.3 and above, so they are good. But you have to come down and check whether the p-values are approximately less than 5%. Once that is done, then you can beautifully confirm that there is a significant situation there. Okay. And I want to believe that Latifa, do you get it? Is it clear? Is it clear?
Yes, I get it, sir. Thank you very much.
All right. So that's how you got to identify all significant values. Now we are ready to go to do the principal component. So let's start. Now in R, there are two functions you can use to do PCA. One is PRINCOMP. PRINCOMP uses correlation matrix, and the other is PRCOMP. That one uses variance covariance matrix. Can you guys hear me? If you can hear me, type yes. Okay, you can hear me, that's fine. Okay, perfect. So let's move on. We are going to use, I do not recommend the using of the variance covariance matrix. Okay, so we are going to use a correlation matrix to do the principal component analysis. So we're going to use the command PRINCOMP. So let's go to R, and then we are going to type this command to generate the principal component result. And then we are going to eat the results. You're going to enjoy that breakfast. So the command we are going to use for, you just want to call it PCA. So you go to R. Let's go to R and type this command there. So I'm typing in command 8, PCA equal to, and then you type PRINCOMP. Okay, PRINCOMP. If at the moment you start typing, depending on your then you will get it popping. And then once you type PRINCOMP, you type the name of the data. And the name of the data is EG. You bring a comma, then type call for correlation. And then you bring T to indicate that you want the correlation true. So you do T to indicate that true. Okay. And then you bring outside the bracket, you bring a semicolon. So we want to quickly summarize the results. So you want it to run the correlation and give you the results. So type summary into brackets. Okay, you type summary into brackets. Then you type PCA, because that's the name of the data we gave here. So we are going to type that same PCA. Then you bring comma, and after comma, you type loadings. Remember the last time we were talking about loadings. Okay. Type loadings. Once you type loadings, then you do equal to true or T, and that's it. So this command is going to give you everything you need about the principal components result. And then we are going to interpret each one of these results. Once you are done with this, type run it or type control N. And ladies and gentlemen, isn't it beautiful? Look there. It starts from here, by the way. And everything below is all you need. And in fact, if this was an exam, that's what I would generate for you. I will generate for you and I'll ask you like 10 questions about this. It looks quite, it looks, some of the things I've eaten down in the other. So I want to run it again so that everything will be nicely packaged. So let me run it again. Excellent, excellent. So you can see that this is the results that you will need. You're going to make some sense out of this result. So this is where the real work begins. So now let's get it. So the first thing you're going to see in the results, and I'll show you because you need to see it with the eye. The first thing you're going to see in the results is that you're going to see that the information is going to be giving you importance. You see the first one, importance of the components. That's the first thing you see. Importance of the component. And for each importance, for each component, you have the standard deviation, the proportion of variance, and the cumulative variance. I'll explain every one of these. Okay. Each one of them we are going to explain. So you're going to have the proportion of variance, the cumulative variance of every single one of the principal components. It's all here. And then finally, you also have the loadings. And this is a matrix. It's like a kind of a correlation matrix between the variable and the component, which we did in class. Theoretically, we did in class. Do you remember? Excellent. So if at any point you don't get it, just let me. So let's try and make sense and find out our first questions. Okay. Our first question. And I'm taking you back to the slides so that we try and make sense of the question. The first question says that what's the proportion of variance accounted for by the first principal component? What is the proportion of variance accounted for by the first principal component? Let's get that first. So let's go to the arrow. Look at the arrow. What is the proportion of variance accounted for by the first principal component? I want somebody to give me the answer before I actually show the answer to see whether somebody can crack it. What is a proportion of variance? That is if you have not copied it from anywhere, but it's coming from your own coconut. Eugene Parkwesi.
Yeah, hello sir. Doc, sorry. So the first proportionate of variance for component 1 is 0.547.
Good, excellent, excellent, very good. Now, advice, you always convert it to two decimal places, and then you put it in percentages. You always convert it to 2 decimal places, and then write it in percentages. So Eugene, even though you are gone, I'll let you do it. So
okay, so the solution is 0.55%.
Say that again.
55, sorry. Solution is 55%, sorry.
Exactly, exactly.
Yes.
Okay, so it is 55%. We are going to interpret it very soon. Okay, so that is 55%. So what is a proportion of variance accounted for by the first principal component here? Okay. And the answer is what? 55%. That's it, 55%. When you look at it, this is the value. Okay, 55%. Now, what is a proportion of variance accounted for by the second principal component in percentage terms? The proportion of variance accounted for by the second principal component. In fact, many of you are already writing the answer, 25%, 25. And that is right here. Now, do you realize that the percentages are falling as you keep going? Okay. Because remember we said that the first principal component accounts for the greatest proportion. Okay, what is a proportion of variance accounted for by the third principal component? By the third principal component. Let me see whether there'll be wonderful write-up. In fact, the way some of you are writing it is, if you write 14.33%, that's wrong. I told you, round it to 2 decimal places and then put that in percentage. So that's 14%. That's 14%. Okay. So do you realize that there were 6 variables? And there are now how many principal components? 6 principal components. Remember we said that the total number of principal components eventually becomes the number of variables. Now let's go back to the first principal component and interpret that. Because I will ask you the same thing. How do you interpret that 55%? How do you interpret that? Who is able to tell us how you interpret that 55%? Who can guess? Who can guess the interpretation of the 55%? What does that mean when it comes to principal component 1? What does that mean? It means that principal component 1 does what? How do you interpret that? Let me see. How do you interpret that? Okay. Oh, Grace. Grace seems to, oh, Grace is gone again. Yeah, this is the fear factor. Okay. Isaac, let's see whether Isaac is ready to rock and roll. Okay. Isaac, see, let's see, what do you have?
Okay, sir. So my understanding is that principal component 1, the 55% means that principal component 1 contributes about 55% of the variance in the data set.
Exactly. That's it. Okay. So it means that principal component 1, okay, explains 55% of the variation or the variability observed in the original data set. Okay. So when you look at the original data set, much of the information content can be explained by principal component 1 55% of the time. Okay. So that is the way you interpret it. Now, who can then interpret the principal component 2? See how life is sweet. Principal component 2, especially when the gates to paradise has been opened, now it becomes easier for you to enter. Who can interpret the principal component 2? Okay. And please don't use the word variance. We want another word. All right, Derek.
Okay, Doc. So this means that 25% of the variability in the original data set is explained by the PC2.
All right. So 25% of the information content or all the variances you observe in the data set is explained by principal. But I don't need to ask you to explain the principal component 3. Okay. But let's look at the next question. Let's look at the next question here. The next question says, what is the cumulative proportion of variance? Now, this is important. What is the cumulative proportion of variance accounted for by the first principal component? Who can tell us that? Let me take it back to the data. What is the cumulative proportion of variance accounted for by the first principal component? Who will give us the answer to that? Let's see. David has written 55%. I'm sure the rest of you will know that. Okay. So this one is good. Let me ask you another question. I think this one. What is the cumulative proportion of variance accounted for by the third principal component? Who can tell me that? the cumulative proportion of variance accounted for by the third. Oh, I was going to take Reuben. Yes, Reuben. By the third principal component. Okay, the proportion of variance accounted for by the third principal component. What would that be? What would that be? I think Rubin's network is. So let me go to comfort. What would that be? Cumulative
94%.
Again.
94%.
94% is the right answer. Okay. 94% is a proportion of variance accounted for by the third principal component. Now, guys, listen. I can easily, and I know that I will easily delete that cumulative proportion. Okay. So I can delete that section, everything inside that cumulative proportion. I'll delete it. And even if I delete it, you should be able to calculate it. Do you know that? Yeah. You should be able to calculate it because you know that the only way to get the next one is to add the first one to the second one. So when you add the second proportion of variance to the first proportion of variance, that will give you the second cumulative proportion. When you add the third to the second to the first, that will give you the third cumulative proportion. So I'm sure you get a picture. So it's very important to note that you will not get a cumulative proportion. But you should know there's a difference between the cumulative proportion and the word total. Because sometimes I will not use the word cumulative proportion. Oh, believe me, I won't. Sometimes I will use a word like, total. What is the total proportion of variance? And I'm telling you, last time I did that, some people really just didn't get it. They thought it was the same as the variance I was asking of. But when I say what is the total variance or the total proportion of variance accounted for by the second principal component, you should be able to correct. So now let me ask one of you, who will be able to interpret the proportion of variance accounted for by the second principal component? Who will be able to interpret that for me? Who will be able to interpret the proportion of variance accounted for by the second principal component? Who will be able to explain that? It's here, but I want you to be able to. Who will be able to explain the proportion of variance accounted for by the second principal component? Priscilla.
Hello, Doc, please, can you hear me?
Yeah.
Okay, so I think 25% of the variability in the data set can be explained by the principal component 2.
Say that again.
I'm saying that 25% of the variations can be explained by the PC2.
All right. Okay. I want to be sure whether I asked the wrong question or you gave the wrong answer. Okay. What I was saying is that I was asking you, how do you interpret the total proportion of variance accounted for by the second principal component? Is that the answer you gave? The answer you gave. Priscilla, is that the answer?
Then I think it's 80%.
So explain what you're saying.
If that is the question, then I think the answer is 80% rather.
So say it, speak in a language and let me understand now. Explain, interpret it then.
Okay, so the cumulative variance to principal component 2 can explain 80% of the cumulative variances in the data set.
All right, okay.
If I'm not mistaken.
Yeah, I just didn't want to use the word cumulative, but that's okay. That's fine. You got it. Okay, get it. I think that. So the key point is that the principal component 2 accounts for 80% of the total variability in the original data set. The word is 80% of the total variability. 80% is important. And then total is important. And that is this. Okay? Counts for 80% of the total variability in the original data set. Please remember that if it was in an exam, these values will not be there. So you would have to calculate these values yourself and then use them to interpret them as well. And in your interpretation, it's got to be clear that you are talking about cumulative proportion or total proportion, not just proportion, but total. Okay. Now let's move on and go to the next question. Now, it's not shown here, but every principal component has a standard deviation. Well, that one is shown here. You can see that in the let me take you back to even this. Okay. Every principal component has a standard deviation. We've spoken about the proportion and then the cumulative proportion, but every one of them has got a standard deviation. And please note the relationship between the standard deviation and then the eigenvalues. The standard deviation is the square root of the eigenvalues. Okay, the eigenvalues are the variances. The eigenvectors are the standard deviation. Okay. So it's very important to get some of those things. So the standard deviation is the square root of the eigenvalues. So if I tell you to find the eigenvalues of the first principal component, oh, you got some people with questions here. Okay, Grace, you have a question? Oh. Yeah, Grace, you have a question?
Yeah, hello, Doc.
Yeah, go ahead.
Please, I'm saying kindly go over what you just said about the standard deviation and the eigenvalues.
Okay, that's your question. Yes, Priscilla, you have a question. Priscilla, do you also have a question? Let me come to Michael. Priscilla, I don't know, this thing is not opening. Michael, go ahead.
Yes, Doc. Please, with just before we were talking about the eigenvalues, I wanted to find out, since it's cumulative, since we're talking about cumulative variation, is it just the second PCA that accounts for the 80%, or is both the first and then the second?
What do you think? Answer that first.
Doc, I think it's both of them, since
You're correct.
we are
Don't
using
sense
the
it.
cumulative.
You're correct. Don't sense it. So you've answered your question. All right. So that's it. All right. So I was saying that the principal component, each one of them has got an eigenvalue. That's what I was saying. Each one of them has an eigenvalue. And then the eigenvalue, this is what you see there. The eigenvalue, okay, is a square of the standard deviation. And so the standard deviation is the square root of the eigenvalue. Okay. The eigenvalue is the variance. And you all know that the standard deviation is the square root of the variance. And the variance is the square of the standard deviation. And since the variance and the eigenvalues are the same, it means that the eigenvalues are the square root of the standard deviation. In other words, I will not ask you to calculate the variance of the standard deviation, because that makes it too easy. But I will ask you to find the eigenvalues. I'll ask you to find the eigenvalues of each principal component. Do you get it? So when you go to each one here, and I ask you find the eigenvalues of each principal component, you should know that that is the square of the standard deviation. That is a square of the standard deviation. So I can tell you to find the eigenvalues of all the principal components. Oh, that is going to be wow. So you go and then find all of these for me. Or I can say that find the eigenvalues of the first three principal components. So now I've limited you. The first three principal components. Find the eigenvalues. And then we are there. But the most important thing is you understanding that the eigenvalues are the squares of the standard deviation. And since the standard deviation is already given, I will not ask you to tell me the standard deviation of the first three principal components. No, I'd rather ask you to tell me the eigenvalues, which is the same, the variances. Okay. So I guess you get a picture. Okay. So now let's go to one of these questions. Okay. So the question is, find the eigenvalues of the first and the second principal components. Find the eigenvalues of the first and second principal components. So now you see them here. What are the answers? Find the eigenvalues of the first and the second principal component. So what are the eigenvalues of these two principal components? Who can give me the first answer? Okay, Comfort says the first one is 3.28. What about the second one? It's the first and the second I want. What are the second one? I want both first and second. So Paul, Grace, the second is 1.51. So this is where you just take your calculator and just calculate the answers. Okay. Somebody says 1.54. Is it 1.51 or 1.54? This is where your decimalisms are important. Now another person says 5.12. So if you tell me that from slide, it means you are copying things from slide. Don't copy things from slide. Okay. What is the proper eigenvalues for the first principal component and the second principal component? Okay, always correct it to 2 decimal places. Okay, and then you now use that corrected decimal to do your working. So what is the value? What is the value? Now I get 2 different answers again. Abba. Some of you are confused. Is it 1.52 or 1.51? Okay, if you use my own, you might get it wrong. Okay, so you have to be systematic. So this is, so you get 1.23, then you square. So you round it to 2 decimal places before you square it. And when you square it, you get 1.51, also rounded. So you're supposed to get 3.28, which I think all of you had. And then you also get 1.51 instead of 5.2. Is it 5.1 or 5.2? Somebody is still writing 5.2. Do I have to go and take on my calculator and then calculate it? Let me see. The answer is 1.51. If you type it into your calculator, you will get exactly 1.51. All right. So that is how you find the eigenvalues. Okay. That's how you find the eigenvalues. Ernest, Sosu, you have a question.
If you type the whole thing into the calculator, it's like...
Don't type the whole thing into the calculator. You remember I said round it to 2 decimal before you type.
Okay, okay, sorry.
All right, okay. So always round it, always round it. Round before you work it with it. Round before you work with it. Okay. All right, let's go to the next one, and they're probably the most critical one. You remember we spoke about loadings or the importance or the weights. You remember? These are also called the eigenvectors. And we said that there is a correlation between the original value and then the principal component. And these correlations are reflected in the weights. These weights are called loadings. These weights are called loadings. And that is the part of the table that you saw, this part, the down part of this table, the loadings. So if you look at the loading, it is exhibiting the intercorrelation between each variable, as the original variable, and each principal component. Now, ladies and gentlemen, this is very critical because this is where people make a mistake. When you are writing an equation of a principal component, you got to use the exact word as it is in the R result. So let's say that we normally write principal components And you and I have been doing this a couple of times. We normally write it as PC1, isn't it? Now you will not write it as PC1 because when you look here, okay, you will see that they've not written it as PC1. They've rather written it as comp, and I mean it, dot 1. Exactly as it is. That is how you are going to exactly write it. You don't change it. Comp.1, comp.2, comp.3, and another. And so when you are using them, you got to use them just as you see them. Basically, that is it. So keep that in mind first, please. Now, let's go ahead and then look at the question we want to address. Okay, and that is, so that table shows the relationship using the correlation. The question you are being asked here is how many new, and this word is very important, how many new principal components that explain the same information as the original 6 variables did this PCA method find? How many new principal, it's a very tricky but very easy question. How many new principal components that explain the same information as the original 6 variables did the PCA method find? Who can tell me? Of course, whatever answer you give, I'll let you justify. How many new principal components did the method find? How many? But if you want to look at the data, this is the data. How many new principal components that explain the same information as the original? When you get to the answer, you smile. Okay. All right. Let me see whether somebody has cracked it. It's 6. Exactly. It's 6. Okay. It's 6. Well, why is that so? Because the thing is that if you ask me how many new principal components, the number of principal components equals to the number of original variables. Okay. So we found 6 new components. That is what the entire method here did find. So it's a question that really, really technically shouldn't be answered, but that's it. We have 6 principal components. All right, now let's go to the important part. Next question. So I want you to look at the loadings again, okay? We're going to be asking some questions there. Now, there's another software called PAST. Okay, that software, I use it to generate a couple of other things, but this time I've decided to focus on R. So let's do it only the R software. So what linear combination, this is the most important one. What linear combination of the original variables account for the largest variance? Correct to 2 decimal places. And this is good question. This is deep question. What linear combination of the original variables accounts, this is important, account for the largest variance? So first question is this. The first question is, which principal components account for the largest variance? That's what you should find out yourself. Which principal components account for the largest variance? Somebody should type it there for me. Which principal component account for the largest variance? Which PC? How was it written in the R? Which PC? Which principal component? Which principal component, first of all, accounts for the largest variance? Which one? It's comp.1, exactly. Okay, that's a principal component one. Comp.1. Okay, now let's go back to the question. You all got it. Okay, the question says, what linear combination of the original variable account for that comp.1? You get a question now. In other words, when you go to comp.1 here, all right, what linear combination, the word linear combination means you're adding them. What linear combination here account for that? So you're going to actually write the principal component equation, okay, and then indicate which variables actually came together to form that comp.1. It's a very powerful question. So how do you do that? And once again, it would be nice to stick to 2 decimal places. So that means that you got to write the principal component equation for the largest one, which is comp dot one. So you got to write comp dot one, because it's a linear combination, it has to be equal to, and there is no intercept. So you take the first variable, and the first variable with its coefficient is 0.49. Correct to 2 decimal places is 0.49. So it's going to be 0.49 var 1. Okay, it's a plus. Then you do minus, the next variable is what? 0.25. It's actually minus 0.25. So you write 0.25 var 2. Okay. Then you keep adding because we are talking about linear combination. So you do plus 0.5450 var. Sorry, ladies and gentlemen, I think you are getting it, aren't you? And so that becomes the linear combination. It's simply a way of trying to say that becomes the equation for the first principal component. So what this means is that each one of these variables, the coefficient, the weights, each one of them tells you the contribution of the variable towards the formation of the principal component one. Okay. That's it. Each of these variables, okay, tells you the contribution. So the first one here is the contribution of variable 1 towards the formation of comp dot 1. This one tells you the contribution, whether it's a negative or positive contribution of variable 2 towards the formation of comp dot 1. I'm sure you get it, don't you? And that becomes the way you should write the principal component, okay, equation. Okay. So this is how, so we are talking about the first equation of the principal component. And like I've indicated here, it's just like the estimated regression equation. So that is what we just deduce from here. This is how you write it beautifully. Now, if I should ask you, what is the estimated equation for the second principal component? I'm sure you can do that. Yeah, I'm sure you can do that. The estimated equation for the second principal. Now, there's some tricky point here that I want you to know. I don't want you to do the second principal component. I want you to do the third principal component. The third principal component, because that one is a little bit tricky there. Let me see. Who can raise a hand and step by step walk us through it? How do you write it? How would you have written it? You just say how you would have written it. The third principal component, who can tell us? The third principal component. The third. What is the equation of the third principal component? Okay, so Grace wants to help. So Grace, walk us through it.
So please, yes, thank you. So I would have written comp dot 3 is equal to 0.14 plus 0.22 minus, 0.14 var 1 plus 0.22 var 3 plus minus 0.19 var 4 plus 0.80 var 5 minus 0.51 var 6.
Correct, exactly. The most important thing she omitted, which she should omit, is the third one. Do you guys observe that? So she did not mention anything related to var 2. And that is a critical aspect of what we are discussing. There is no need to incorporate var 2 because there is no loading, there is no weight, no importance attached to variable 2. It means that the importance that was needed to attach to variable 2 by component 3 is not necessary. Excellent. Beautiful. That's how it's supposed to be. Any question on that? Now let's go to the next part. So that is the one I'm more interested in. Okay. All right. Now, let's go to the next question. How many principal components have the power? Okay, you got some questions from people. Latifa, you have a question, go ahead.
Sir, so does that mean the linear equation is the same as the estimated Equation.
Correct.
Okay, thank you, sir.
Watch it, Prempe. You have a question. Watch it, Prempe is gone. So I think that Latifa, you've answered his question for him. All right, so how many principal components have the power to explain the information in the original variables? That question is an important. In other words, now we want to know how many of the principal components we need to select. Now, ladies and gentlemen, whenever you have such a question, like how many principal components, because there are several principal components, in this case, there are 6. Now, we have a heuristics. Okay? We have a kind of a procedural analysis, a hunch, a heuristics. And here is a heuristic. The heuristics is that, and so these are some of the criteria you are going to use to identify how many PCs or how many principal components. You have to take all those principal components whose standard deviations are roughly greater than 1, or whose eigenvalues are roughly greater than 1. That's the first rule. Okay. So when you go to the thing here, which principal components will be captured in this context? Okay. Those with principal components whose values, whose standard deviations are greater than 1. Okay. Which ones would have been, which principal components would have been selected? You can raise your hand and tell me. Or somebody has already written the answers. Comp 1 and Comp 2. Okay, I guess you're all right. Looking at the standard deviation, it would have been Comp 1 and Comp 2 because the standard deviations are greater than 1. Greater than 1. So it's Comp 1 and Comp 2. Okay. That is the first criteria approach. Okay. That's the first approach. Okay. Eunice Awiso, you have a question? Eunice, you have a question? Okay, I'm trying to unmute you. So if it doesn't, it appears that your situation is, so Eunice, if you can type your question in there. Okay, whilst I go to Eugene. I'm not able to crack you, Eunice. Yeah, Eugene.
Thank you, Doc. So if the value for the component is almost approximately to 1, and that's the only value available in the whole standard deviation.
That won't happen.
Okay, thank you.
All right, okay. Like I said, there was somebody who had a question. Let me see whether she's typed a question. Okay, she hasn't. All right, so that is it. Using this criteria, it means that we'll go with 2 components, okay? But so hang on a minute, that's not the only one. Another thing is that you can use the elbow effect of the square plot or the biplot. Now let's go and then have a feel of this. So first, using the standard deviation, okay, the first 2 principal components have eigenvalues of greater than 1. Now, if you go and check the standard deviation and you check the eigenvalues, they are all greater than 1. Okay, that's the first thing. Now, let's look at the elbow effect of the square plot. Okay. We've already explained this the last time. We said that the square plot tells you the percentage of the variability in the data set explained by each of the principal components. And the idea is that it's going to help you find out which components are needed to summarize the data. Okay. Boache, you have a question?
Yes, Doc. Please, I want clarification. You made mention that the components that has more than 1 standard eigenvalue are to be considered as part of that contribute high information. But I thought the eigenvalues were related to the variance, that the standard square root of the square of the standard deviation.
Yeah, it doesn't matter. It doesn't matter. Okay, it is a square of the standard deviation. Both of them must be greater than 1. The fact that it's a square doesn't mean that it won't be greater than 1. No. And the fact that 1 is a square root of the other doesn't mean that it won't also be greater than 1. So what you want to do is to go and just calculate and be sure. And you see that they are all greater than 1. And the next one will not.
Okay, all right. Thank you, sir.
Okay, that will convince you. So if you check the 3rd principal component, okay, if you go and check the 3rd principal component and you check its eigenvalue, square this variable,
Yes.
And then you check its eigenvalue. You see that it's less than 1, isn't it?
Yes.
Exactly. It's not magic. It's not magic at that. Oh, because you are the square, then that one, will be different. It won't.
All right. Thank you, sir.
So let's go to the script plot. Now we are going to draw the script plot in R. And the way to draw it is type plots, PCA, type, and all that. Okay, so let's go to the R and just generate our plot. Okay, so you type plots, and then into bracket the name of the principal component, and that was PCA. That was the name we used. So you do that name of the principal component. Then you want it to be in lines. Okay, so after that you type. Okay, and then once you do type, we want the type to be equal to lines. So we want it to be in lines. In other words, we want to draw a line, okay, and we want to give it a color. So you do comma, and then type color equal to red. You can use any color. Okay, and then you do comma, and then after doing comma, you can add a line width. Okay, LWD, the line width, and then give it like say 6 or 4. Okay. The one in the slide is 4. I'm just using 6 here. So look on the right of the plot section here. The results is going to pop out. So you just generate the script plot, and boom. Now you can see the script plot. Okay. All right, Boachi, you have a question?
Yes, Doc. Thank you so much, Doc. My network is so much not stable, so I don't know if you have all this in your this in the YouTube, because I go, I come.
Don't worry,
and I go.
you'll get everything.
Yes, please, sir.
All right.
Doc, thank you so much.
So when you look at the PCA graph here, okay, when you look at the graph, this is it. Are you able to determine the elbow effect? Sometimes if you don't open your eyes, you might not get it. Do you realize the elbow effect? Where does the elbow effect occur? Where does it occur? Is it occurring at PC2 or PC3? If you look at it, where does the curve begins to bend first time? Look at it. That is the elbow. That is the elbow. And you can also do the script plot. So let me do the script plot. Okay. Another way of drawing the script plot. Sometimes you can do the script plot in different drawing. Let me type this one. Okay. And then do PCA. See, this one gives you the histogram. Okay. But that one is not that nice. So it's nice to use the first one, which is this. There you get the picture very nicely. So let's go to the question we were asking. The question is, using the elbow effect, how many factors are extractable? How many principal components are extractable using this elbow effect? What will you say? Does the elbow effect confirm components of 3 or components of 2? What do you say? 3 or 2? Priscilla says 3. What do you say? Letitia says 2. What do you say? Julian says 2. What do you say? Ellen, Grace, all of them are saying 2. Anna says 2. Eugene says 2. Meda, 2. You are there. You are not talking. You are also there. Opele, what is it? Is it 2 or 3? Fred, Kennedy, Comfort, Jeffrey, what are you saying? Henry says 2. Okay. Nuruddin, you're saying 2. Richmond, say some, because you won't die. You won't die if you type. Okay, you won't die. Selena says 2. So let me tell you why 2 is the right answer. Because the beginning of the elbow happens at point 2. Even though component 3, it's on the same line, the bending has already happened at 2. It is where the burning begins. That's what we are talking about. And so there are 2 components that are extractable. Okay, 2 components are extractable. Okay. So using this elbow effect, we can say that, okay, 2 components are. Now, we've already explained this. After the curve flattens to out, the principal components can be regarded as insignificant. There's something we call the Joliffe cutoff point. Okay, that will tell you the number of significant principal components. Okay. And he says that principal components with eigenvalues less than this cutoff point he is given can be considered as insignificant. Okay. But the basic thing is to go the simple way. All right. Okay, so basically, in this very case, the point of separation, which is the elbow effect, it looks like the slope levels out after principal component 2. So we can say that only 2 components are extractable. That's what we can say for this very one. Now, it doesn't mean that every time in this world is going to be only 2 components. Remember, life is not a straight line. Finish. Let's go to the very last one for today. The very last one for today. Unless there's a question. I think somebody has a question. Comfort, you have a question?
Yes, Doc. Please, with the one we just did, are we going to have options or we have to use?
No, you have to select. You have to choose your own. No option. No multiple choice.
No. Like, I mean, you can use, we know you can use the standard deviation, but if you are not very good at mathematics like me, will there be
you will be told what specific approach you should use.
Wow.
And many a times you'll be told to use all of the approaches. All right, you got the answer. I think your wow doesn't make, well, it means that you are happy with the answer. So that's why you say wow. Okay. All right, the last thing to do is that after selecting the number of components, the last and the final thing to do is to now identify which variables will be seated into which component. Which variables will be seated, will be inside the hull of which component. That is a biplot job. That is a job of the biplot. So the biplot shows both the loadings and then the variables for the 2 selected components. The biplot is powerful. It's an enhanced scatter plot that shows the data along with the projections of the original variables and how these project onto the first 2 principal components. In this case, we are using principal components. Okay, in this case, we are using principal component. Wonderful. Oh, dear. So now let's look at this. Now we are going to draw the biplots, and the way we are going to do it is just type biplot into brackets PCA. So let's go to our R, okay, and type biplot. But sometimes the moment you start typing, it will show PCA, okay, and then you will want a color. So let's do comma COL for color equal to, and then what color are we using? Okay, let's say brown, blue, because there are 2 different components. Okay, so because there are 2 different components, we are going to select 2 different colors. So in the slides, you have brown and blue. I'm going to use color green as the first one, and then I will do a comma and then do color blue. Okay. So I'm using color green and blue. You can use anything you want. Now, once you click, oh, okay, so something is wrong. Let me just confirm. Oh, you're supposed to bring a concatenation here. You're supposed to bring COL concatenation. Okay, you have to concatenate it before. So you get PCA, and then you close the bracket again. And then now let's run it. You see, when I did the first one, the results didn't show. And sometimes once the results don't show, you have to just read the error. The error, it says error in Biplot, blah, 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 blah. And then it shows length of choices must be 2. So clearly I realized you needed a concatenation. So that's how you do it. And then you run. This is it. This is the graph that you can see beautifully there. So look at this graph. So the graph here is showing some beautiful, results there. Now you can see, now, first of all, in your mind, listen carefully. This graph, this biplot, is a very funny graph. And what you see is always an inverse of what you should not see. So I want you to note some few things. What you see is always an inverse of what you should not see. So when you look at variables 2, 6, and 5, you can see that they are all kind of grouped into one section. Do you observe that? And then variables 1, 2, and 3 also seems to be grouped into another section. So that's the first thing you want to notice there. Okay. Now, variables, so in order to get to know which variables are with another variable, which variables are kind of meeting another variable, the question you need to ask yourself is, where is a component? Where is a component? So look at what I have drawn here. You can get it even differently if you have to do something else. Okay. So look at it. Now, if you look at variable 1, 2, and 3, the whole idea is that they will form one group. Okay, they will form one group. Keep that in mind. They will form one group. And then variable 2, 5, and 6 will also form one group. You get it? Okay, because of the way they are grouped. Okay, so that's the first thing. And the question now becomes, which one becomes component 1 and which one becomes component 2? I know the answer because I've looked at it, because I now quickly can see. But you can't only use the graph to know which ones will be in component 1 and which ones will be in component 2. You can't only use the graph. So in order to find which one will be in component 1 and component 2, guys, please listen. Go back and look at all previous results, especially the results on loadings. So look here, you see the results on loadings. And then look at component 1. All right, look at component 1. This is very important, and I hope and pray that you are listening and you are following me with every muscle inside of your body. So if you look at component 1, and I just want to identify that component. If you look at component 1, you will notice some variables that are under component 1. And watch the variables on the right here. You have variable 1 inside this, and variable 2 there, and variable 3. So come to component 1. Do we see variable 1 there? Yes, we have got variable 1 there. Look at the value. Do we have variable 2 there? No, we don't have variable 2. We have variable 4, isn't it? We have variable 4 because variable 2 is on the top here. So variable 4, you now highlight variable 4. All right. And then the last variable is variable 3. So you also highlight variable 3. Now watch carefully these numbers, and you will see that they are the biggest 3 numbers, are they not? Are they not? They are the biggest 3 numbers under component 1. Okay, and they are the ones that have grouped themselves on the right as well, on the right here as well. Okay, they are the ones that have done that. So they are going to definitely be forming component 1. Okay, now let's go to component 2 and check. Component 2, we believe that this one here is component 2. Which variables are there? Come to this. Come to the loadings. Okay, come to the loadings. Now let's see component 2. Okay, let's see component 2. So this is component 2 here. Okay. And when you look at component 2, which variables are we expecting? We see variable 2. Okay. So you can see now variable 2 is bigger 0.67. Okay, that's the loading. The next one we see in the box is variable 5. So let's check variable 5. That is also 0.29. And then we have variable 6. That is also 0.5. Now, let me tell you why these variables 2, 5, 6 will definitely form component 2. Because when you take the first one, which is 0.65, sorry, 0.67, 0.67, when you compare it with component 1 variables, it's even negative 0.25. So it means that the winner will be the 0.67 in absolute terms. When you look at variable 3, okay, variable 3, which one will component 1 be and component 2 be? It will go to component 1 because component 1 is 0.5 and component 2 is 0.2. So no wonder it went to component 1. And then variable 4, that one is also 0.5, is bigger than the 0.21, which is for component 2. And then if you look at the last two variables, okay, if you look at the last two variables, there's a bit of a battle, especially for variable 6. As for, for variable 5. As for variable 6, look at it, there's no difference because it's clearly going to component 2. But look at variable 5. It appears that component 1 should rather have taken the 10. But why is it not going to be that one? Because come back here, come back to the table, the graph, you will see that variable 5 was categorized under 2 and 6. It was grouped under 2 and 6. So even though it appears that variable 5 is it is not, because it is far away from component 1 situation when you look at the biplot. So the beauty is that the biplot should be used in conjunction. The biplot is the winner here. It should be used in conjunction with the loadings, and then you are able to get the beautiful answer there. I hope you get it. So this is the reason why we say that the entire analysis, it is for the variables on the left section here is for component 2, and the variables on the right section is for component 1. Okay. So on the basis of this, let's go to our results. These are results which shows even slightly different things. Many graphs will show slightly different, but you see that the groupings will be the same. Okay. So if you look at this, the groupings, okay, they are all grouping 2, 5, and 6 are grouped together. Okay. And then when you look at this, another graph to the groupings were also like that. So let's go to the final question that brought us here. The question was, using the biplot and any other previous analysis, just as I did, which variables project onto which component? Well, here's the answer. The variables that project onto component 1 are variables 1, 3, and 4. And the variables that project onto component 2 are variables 2, 5, and 6. Okay. So in general, the above data set of 6 variables may be explained by 2P, principal components. And of course, once you know that there are 2 components that are dealing, now you can give them a name. If it is a practical work, okay, you can form a name for them. And this is why sometimes you create a name, a proper name. Then you can now go and use this whole thing in a regression. So principal components is like an exploratory analysis. And then you can now use it for further regression. Next time, we are going to continue and now do factor analysis. Okay. So ladies and gentlemen, that brings us to the end of the entire